All right, for today's lesson, we are going to use some well-known power series that we have generated from the other examples we've done on Taylor and Maclaurin series to do some examples. All right, so here's a table of some of the ones we've already done. So reciprocal function, we have 1 over 1 plus x from our geometric series, natural log, exponential, sine, cosine, arctan, arcsine, and then our binomial 1 plus x to the power of k. And here's the various intervals of convergence as well. So our first example is to find the power series for the function f of x equals cosine of square root of x. So I'm going to look to my cosine function here on my table, and that's going to be what we're going to be using. So let's write that down. So cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, ... The general term for that is negative 1 to the n over x to the 2n over 2n factorial. And that pattern continues. And my interval of convergence is negative infinity to infinity for cosine of x. For cosine of the square root of x, essentially all I'm doing is I'm replacing all of the x's in this formula with square root of x. So cosine of square root of x is going to equal 1 minus the square root of x squared over 2 factorial plus the square root of x to the 4th over 4 factorial minus the square root of x to the 6th over 6 factorial, so on and so forth. And my general term is negative 1 to the n over the square root of x to the 2n over 2n factorial. And when I simplify that, I'm going to get 1 minus x over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial after everything cancels. So the general term would be negative 1 to the n, and the x and the square root and the 2 cancel, so I just get times x to the n over 2n factorial. And now I need to think about the interval of convergence for this one, or just for which values of x it converges for. And so it's not necessarily there's not like a radius of convergence for this one. Because I have this square root of x, I need to think about the domain of the square root of x, which is just all x greater than or equal to 0. So this converges for all x greater than or equal to 0, since that's the domain of cosine of square root of x, specifically looking at that inner function for that one. All right, our next example says find the first 3 non-zero terms of the Maclaurin series e to the x times arctan of x. So for this one, what I'm going to do is I am going to use both the power series for e to the x and arctan of x. So I'm going to go up to the top, copy those down. So we have e to the x is right here, and arctan of x is right here. So when I multiply those two together, I get e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so forth. And arctan of x is x minus x cubed over 3 plus x to the 5th over 5 minus so on and so forth. Okay. Now I only want the first 3 non-zero terms, which is helpful. So I'm just going to FOIL this. So when I FOIL the 1, I get x minus x cubed over 3 plus x to the 5th over 5, and so on and so forth. And I left space for my even powers. So here I only have odd powers of x, so I left some space for my even degree functions. So when I distribute the x, then I'm going to get x squared minus x to the 4th over 3 plus x to the 6th over 5, and so on and so forth. When I distribute my next term, the x squared over 2 factorial, my first term is going to be x cubed over 2 factorial, and my next term is going to be negative x to the 5th over 3 times 2 factorial. And then I'm going to have a x to the 7th. We actually probably don't need that because we're only looking for the first 3. And then as we see our next term, when I distribute the x cubed, my first term is going to be x to the 4th over 3 factorial. And then I'm going to have negative x to the 6th over 3 times 3 factorial. And when I add these up, pattern continues, of course, but when I add these up, I only want the first 3 positive terms. So I'm just going to add up the linear term, quadratic term, and cubic terms. So the linear term is x. My quadratic term is x squared. And my cubic term is when I add negative x cubed over 3 plus x cubed over 2 factorial, which is just 2. So common denominator is 6 there. So I end up with a positive 1/6 x cubed. And then the pattern would continue. Okay, so you would continue to add the degrees of 4 and so on and so forth. But those are just the first 3 non-zero terms of the Maclaurin series, e to the x arctan of x. Okay, our next example says use a power series to approximate the integral from 0 to 1 of e to the negative x squared dx with an error of less than 0.01. Okay, so let's figure out how we're going to use a power series for this one. So we're going to go ahead and use e to the x again. And so the power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so forth. So the power series for e to the negative x squared, I'm just replacing my x's with negative x squared. So I get 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus so on and so forth. So then when I do my integral from 0 to 1 of e to the negative x squared dx, that's the same thing as the integral from 0 to 1 of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial, and so on and so forth. So if I integrate term by term, I get x minus x cubed divided by 3 plus x to the 5th divided by 5 times 2 factorial minus x to the 7th divided by 7 times 3 factorial plus x to the 9th divided by 9 times 4 factorial. And I want to evaluate those from 0 to 1. And when I plug in 0, I just get 0, so I don't need to worry about the term I'm subtracting. So I am just going to plug in 1. So when I plug in 1, I get 1 minus a third plus a tenth minus 142 plus 216th, okay, and so on and so forth. So we want to talk about error, which is the remainder, right? So we're thinking about remainders here. And so when we talk about alternating series, the remainder of an alternating series, let's refresh our memory. So alternating series remainder says that the absolute value of the total sum minus my approximate, which is the sum of the first n terms, is equal to the remainder. Okay, and error is just absolute value of remainder. And that in an alternating series, that is going to be less than or equal to my next term. Okay? So I need to basically figure out, when does this term become less than 100th? Right? That's what I need to figure out. Okay? So if I look at these terms that I've written down so far, and I approximate them, we see that we have 1 minus 0.3 repeating plus a tenth, and then 142 is approximately 0.0238. We're still not less than 100th yet, but 216th is less than 100th. Okay, so this is less than 100th, which is nice. So that's going to be my error. So then this, from 1 to negative 142, this is my approximation, which is about 74 hundredths. Okay? And then this right here would be my error, the 1 over 216th. All right? And those are the examples for today. So go ahead and try your homework.